Hello, my name is Gabriela. I am a PhD student at Imperial and I am going to talk about symbolic analysis of event-driven web applications. This is joint work with José Fragoso Santos, Petar Maksimović and Philippa Gardner. I will start with an example from Stack Overflow. Please don't worry about understanding the code in detail. Essentially, this code reads a file line by line, also performing some operations asynchronously. However, the developer is struggling to have control over the order in which these operations are executed. This seems to be a common difficulty among developers when executing asynchronous code. We should note that asynchronous JavaScript code often makes use of multiple event-based APIs. For instance, this code uses DOM events indirectly when calling the on function for event handler registration. It also uses promises, which provide a built-in mechanism for handling asynchronous execution in JavaScript. As if that weren't enough, it also uses the async await API. So, in order to reason about this example, we have to be able to reason about these three sophisticated event-based APIs. There has been a lot of work on reasoning about programs that interact with the DOM, spanning different techniques, such as information flow control, formal semantics, symbolic execution. And there has also been some work on JavaScript promises, especially in the context of dynamic analysis and formal semantics. Now the question is, how could we be able to reason about programs that manipulate not a single, but multiple event-based APIs? We implement our solution as JAVERT.CLICK, a new tool for symbolic execution of event-driven web applications. We started from JAVERT 2.0, our symbolic execution tool for JavaScript, which we presented at Popo 19. JAVERT 2.0 supports three types of analysis: whole program symbolic testing, verification, and also automatic compositional testing based on by abduction. In this paper, we focus only on symbolic testing. So, given a JavaScript program written in ES5 strict, which is the JavaScript version supported by JAVERT 2.0, the JS2Gisel compiler compiles the JavaScript program to Gisel, our intermediate language for JavaScript analysis. The Gisel program is then given as input to the symbolic execution engine of JAVERT 2.0. We can perform the analysis using both a concrete or a symbolic JavaScript memory model. We also provide a correctness result that guarantees, for instance, that there are no false positive bug reports. JAVERT.CLICK extends JAVERT 2.0 with a trusted event-related infrastructure. Essentially, this infrastructure consists of an event semantics, which is parametric on an underlying language L, and adds, on top of the language, specific primitives to deal with operations for event manipulation, such as handler registration and event dispatch. The infrastructure also comes with trusted JavaScript reference implementations of DOM Core Level 1, DOM UI events, JavaScript promises, and JavaScript async await. These implementations are trusted in the sense that they follow the API standards and are also tested against the official test suites, passing all applicable tests. Now, let's see how this works. So, given a JavaScript program, we first transpile it to ES5 strict. We then compile the resulting program to Gisel, which is our intermediate language for JavaScript. And together with the input program, we also compile our JavaScript reference implementations of the DOM Core Level 1, DOM UI events, JavaScript promises, and JavaScript async await. We then analyze the compiled Gisel program using our event semantics, parameterized with the Gisel symbolic semantics. I will now move on to the description of our event semantics. Making the event semantics parametric on the underlying language semantics is important for achieving modularity. The event semantics state, omega, is a triple that contains a configuration of the underlying language that is opaque to the event semantics, a handler register that maps events to handlers, and finally a handler's queue that contains the handlers yet to be executed. So, the event semantics takes as input a transition of the underlying language semantics and produces a transition of the event semantics. These transitions can be either concrete or symbolic. The job of the event semantics is mostly to manipulate the handler register and the handler's queue. It will usually update the language configuration simply following the underlying language semantics. Let's now see an example making use of the event semantics. But before going into detail, we should note that this example makes use of both symbolic execution primitives that are provided by JAVERT 2.0 and also makes use of event primitives that are provided by JAVERT.CLICK. The SymString primitive allows the creation of symbolic strings. The addHandler primitive associates an event with a handler. The sDispatch primitives executes the handlers of the given event immediately and then proceeds with the current computation. And finally, the aDispatch primitive registers the handlers of the current event to be executed once the computation has finished. We will show the step-by-step symbolic execution of the code on the left. We start with the initial state that contains the initial language configuration, the empty handler register, and also an empty handler's queue. We then add the two handlers. This only changes the handler register. As you can see in the slide, the language configuration and the handler's queue don't change, but in the handler register, the event init is now mapped to the list containing h1, and the print event is now mapped to the list containing h2. We then have the asynchronous and synchronous dispatches, and because E1 and E2 are symbolic, the execution branches here. Let's first consider the case in which E1 is the string print and E2 is the string init. This means implicitly that we add a constraint to the path condition of the language configuration, assuming these values for E1 and E2. In this case, we dispatch the print event asynchronously, so the handler h2 goes to the back of the handler's queue. We then dispatch init synchronously, so h1 is placed at the front of the queue and is executed immediately. You can see that the handler's queue is now the list containing h1 and h2. As h1 is executed before h2, we are fine here because we first initialize the variable person and then print the value of the property name. However, for some of the branches, the execution leads to a type error. Let's now consider the case in which E2 is the string print. The value of E1 doesn't matter in this case, as the handler h2 is in queued and executed immediately. Observe that in the handler's queue we now have h2 placed at the front. So, as we haven't executed the handler h1 first, the variable person is still set to undefined, leading to a type error when the program tries to access the name property. We provide soundness and completeness guarantees for our symbolic event semantics with respect to our concrete semantics. Our directed soundness property guarantees that each symbolic trace over-approximates all of the concrete traces that follow its execution path. So, assuming that we have a symbolic transition and a concrete transition of the event semantics, if we know that the initial concrete state is in the interpretations of the initial symbolic state filtered by the final path condition, we can guarantee that the final concrete state is in the interpretations of the final symbolic state. We define directed completeness as every symbolic trace having at least one concretization. This is important to guarantee that there are no false positive bug reports. So, if a bug happens symbolically, there must be a corresponding concrete trace that triggers the bug. Recall that our event semantics is parametric in an underlying language. We then guarantee the soundness and completeness of the symbolic event semantics, assuming that the underlying language symbolic semantics also satisfies directed soundness and directed completeness. So far, I have introduced the event semantics underpinning JAVERT.CLICK and shown how the symbolic engine works. Now, let's focus on the reference implementations. We implemented all these APIs in JavaScript following their respective standards. However, due to time constraints, we will discuss only the DOM UI Events API in detail. I will now show how we map the definitions of the UI Events standard to our reference implementations in JAVERT.CLICK. We split our reference implementation into two levels, JavaScript code and event semantics. For instance, DOM elements and DOM events are both mapped to JavaScript objects. DOM listeners are mapped to JavaScript functions, and DOM event types are mapped to JAVERT.CLICK events. But in order for our event semantics to be independent of the DOM, we do not model the DOM dispatch algorithm directly in the event semantics. Instead, we handle the DOM dispatch entirely in the JavaScript reference implementation. To do this, we implement the DOM dispatch algorithm in JavaScript and register it as the handler of JAVERT.CLICK events. This is a key insight of our approach that allows the event semantics to be entirely independent of the DOM API. Modeling the DOM dispatch in the event semantics would significantly increase the complexity of the semantics. On the left, you can see the JavaScript implementation of the DOM dispatch algorithm, which calls many functions whose code is not inlined in the slide. We are not going into detail, but there are several steps which involve traversing the DOM tree from the root to the target node and vice versa. These steps are all handled at the JavaScript level. An important function used in all phases of the dispatch is the inner invoke function, which is responsible for executing the listeners registered on a given node. This slide shows our JavaScript implementation of the inner invoke function on the left and the pseudocode of the standard on the right. It's clear that our implementation precisely mirrors the pseudocode of the standard. Following the standards line by line is a key element in establishing trust in our analysis infrastructure. We evaluated both the correctness of our reference implementations and the practicality of our symbolic execution engine. Our reference implementations follow their respective standards and were tested against their respective official test suites. The symbolic execution engine was used to test two highly used open source libraries, Cache and PMAP. This is an important contribution of this work, where we proved bounded correctness of functional properties and uncovered 3 real bugs. This table shows the results obtained when testing our reference implementations against their respective official test suites. For each API, we show the number of available tests versus applicable tests. We had to filter some tests that use features that we currently do not support. For instance, for async-await, we filter out 14 tests that use ES6 default arguments and 4 that use ES6 generators. For all the 4 reference implementations, we pass all the applicable tests. We also measure line coverage, except for async-await. In general, the test suites cover almost 100% of the reference implementations. However, we were still able to provide additional tests corresponding to cases that were not covered. The cache library is a highly used jQuery alternative. It makes use of both DOM Core Level 1 and DOM UI events. We use JAVERT.CLICK to prove bounded correctness of functional properties of the events module of cache. One of the tests, for instance, checks that if a single handler has been registered for a given event, then only that handler can be triggered during dispatch. The event in this case is represented as a symbolic string of maximum length 20. And this test, by the way, revealed 2 bugs. We now show one of the bugs found. It happened that in the cache library some events were being redirected during dispatch, causing the correctness property to be violated. In particular, the focus event was actually triggering the focus in event, and the blur event was actually triggering the focus out event. However, this redirection was not taking place for handler addition. So we could add a handler for the focus event, for instance, and it would not be executed during dispatch. JAVERT.CLICK finds the appropriate counter model, so we reported this bug and the cache developers fixed it. In summary, we designed an event semantics that, although relatively simple, is able to capture the essence of 3 event-based APIs, DOM UI events, JavaScript promises, and JavaScript async await. We implemented 4 APIs in JavaScript following their respective standards and tested our reference implementations against the official test suites. We also used JAVERT.CLICK to symbolically test 2 real-world libraries, proving several bounded correctness properties and uncovering existing bugs. We plan to extend this work by targeting other web APIs, such as web workers and postmessage. We would also like to design a policy language for the specification of event sequences. This may allow us to partially automate symbolic text generation. It would also be great to apply JAVERT.CLICK to other real-world libraries, like Preact.js. Finally, we intend to integrate JAVERT.CLICK with Jillian, our group's multi-language platform for symbolic execution. Many thanks for your attention. I am now happy to answer questions.